Alright, so here's a problem where we not only have to draw the influence line, we have to use it in an application to find values of moment and shear given a dead load of a certain value and a live load of this of another value. So the first step in this problem is to find the influence line. So I'll do the negative moment created at A first. So we have to find an influence line for the moment at A. So let's examine the structure quickly. We do have a fixed connection at A. There's a hinge at B, and then a simple support over here. So if I draw the free body diagram for that, I want to find the reaction at A. So remember, my unit load to create these influence lines is going to be moving around. In fact, just to remind you that, I'll just say, it can be at any position X along that structure. Now, can I solve for the moment at A with a single free body diagram of the whole? No. I have 3 reactions at A, 1 at C, so that's kind of indeterminate, but I can take it apart here at the hinge and get 2 free bodies to work it. Okay? So far, so good? So it's going to be a little more complicated in finding the influence line. So the first thing I want to do is I'm trying to find the moment at A. So I'll draw a free body diagram of kind of what's going on here. So here's the 5-meter section, and I'm going to assume a bending moment at A and a shear force at A, even though I'm not going to find the shear force. I'm going to disconnect it here at B, so that would give me a value which I'll just call Bx and By. See that? And then, of course, the right-hand side so I've got equal and opposite Bx and By. See that? And then my reaction at C. Now, I really want to focus on this free body diagram because that's the one that has the moment at A. So I'm going to have to do it twice. Once I'm going to have to do it where my unit load is here on the free body, and then once when it goes to the right-hand side. You see that? So let's do this one first. So, since the only loading on the structure is this unit load, and it's only between 0 and 5, then what's happening on the right-hand side? Nothing. No load, no reactions. So, Cy, By, and Bx are 0. So I transfer those values to here, then I can solve for the moment very quickly. So if I say, excuse me, springtime. So I'm going to sum the moments about A and set them equal to 0. And when I do that, I have my reaction moment, which is negative. I have my unit load, which is creating also a negative moment with a moment arm of X. And that's it, because By is 0. So it looks like in this case, my moment is just equal to negative X. Okay? Now it's going to take me a long time to redraw this, so bear with me. But the next case will be this. So I have, again, my shear and moment at A. I still have Bx and By. And then over here on my right-hand free body diagram, still there. Oh, by the way, I forgot to put the units in. 10 meters, 10 meters, and 5 meters. Then I have these forces, again, equal and opposite. Bx, By, and also Cy. But in this case, my unit load is now here. See that? Now you look at the right-hand side, you can see that these forces are not zero. The only one I'm interested in, though, right now is By. Because that's the only one, when I transfer the value back here, that will create moment about A. So the first thing I need to do is solve for By. How do I solve for By? Take the moment about C. So if I take my moment about C, make sure it's in equilibrium. I need to know this distance here. Well, remember, I'm measuring it as a function of x, so this distance should be the total 15 minus x. So about C, that creates positive moment. 15 minus x is the moment arm. And then I have By, which is also creating positive moment with a moment arm of 10. So I should be able to solve for By. What is By? It looks like it's, I'll just leave it in this form. It looks like it's negative 15 minus x divided by 10. See that? So now I'll put that value here, and I'll solve for the moment about A. You guys following along? Mm-hmm. Okay, so with some moments about A, in that case I have the moment at A I'm looking for. No load this time because it's over here. And I just have By. Now remember, By came out negative, so it's actually going down. Okay, so that creates negative moment. So I have negative the force, and what's the moment arm? 5. So I can solve for the moment. If I solve for the moment, I get this. This 5 will make this a 2, right? So I should end up with 15 minus x over 2. And there's my second expression. Okay? So now we can come back and we'll draw the influence line. So I'll come over here and I'll make my ordinate again, the moment at A, and then we'll see how that varies over the length. And I'll worry about 5 and 10. So from 0 to 5, I'm plotting this equation, which is minus x. So when x is 0, the moment is 0. When x is 5, what happens? It's negative 5. Like that. So this will have a value of negative 5. Now from 5 to 15, I have to deal with this equation. So I'll just put in 5 here. I got 15 minus 5 is 10. 10 divided by 2 is, hey, it's minus 5. Matches. And when I put in x equal 15, I get 0. So there's my influence line. A lot of work, but there it is. So what do we do now? Well, the question now says, what's the maximum negative moment? Well, it turns out all the moment is going to be negative. Let's do the dead load first. So 1.5 kilonewton per meter. I should have reminded you what these dimensions were. So for dead load, actually a dead uniform load, what do? Well, we take the area under the influence line times the value of the load. So the value of the load is 1.5 kilonewton per meter times the area of this. And that area is triangle, so it's 1/2 the base. The base is 15 meters. And what's the height? -5 meters. Oh, I forgot. This has units of meters. I lost my unit along the way. See the unit of meter? I just left it off. Sorry about that. So now you get kilonewtons divided, 1 meter cancels, you get kilonewton meters, which is a moment. And I don't know what that is. You guys have to help me with that real quick. What's 1.5 divided by 2 times 15 times 5? It's going to be negative.
So you don't have to look at the smaller triangle on the left side. Is that not 2 separate triangles?
Yeah, but the area of a triangle is always 1/2 base times height.
Is that not 2 different triangles?
But there's the height of the triangle.
Yeah.
There's the base of the triangle.
What's in there? 56.25.
What'd you get?
Negative.
Yeah, negative what?
25.
There's a difference.
I can't hear the numbers. What?
56.25.
56.25?
Yes.
He'd already written the negative. That's why I said 50.
I kind of got wedged in there. So there's the part, there's that part. Now what about the concentrated load? Well, that has a value of 10 kilonewtons. So what's the maximum value of the ordinate on the graph? -5. So you'll take your 10 kilonewton times -5 meters. Will give you an additional, let's see if I can calculate that, 50 kilonewton meters. And of course you just add those two together to get the total, which would be -106.25 kilonewton meters. So that's the maximum moment that will occur at A due to our dead load being applied to the whole structure and our moving live load. So any questions about that? Isn't this exciting?
Yeah.
Too excited.
Let's see, who can I pick on? Mr. Romero, what's the definition of an influence line?
An influence line is a variation of the reaction, shear moment, and deflection at a specific point due to moving load.
Due to a moving load. Excellent. I like that.
All right.